So I kind of remembered that's where I came across the blog series, and that's an answer from James Wooden on the quantum computing stack exchange. What is surface code? And I think that this is definitely going. Oh, wait a second. There's some more detailed explanations. Okay, let me check that quickly because I checked all these other papers, and this seems to go one level too deeper or too far away from my interest right now. So I might park the topic here, but I see there's topological quantum memory paper. That's a monster paper. 40 pages. Oh my god. Planar codes. There's a bunch of stuff in here. Dives into all this. Okay. And oh, sorry, you're not seeing that. My bad, because I'm just recording the tab. So this is 40 pages. That's the paper that I was just taking a look at, and this just cool. A bunch of stuff in here. Then we've got also this other paper, which I'm gonna. That's basically surface codes towards practical large-scale quantum computation. Because I remember seeing those quickly before going to the blog posts. Yeah, because I remember this. Okay. Single qubit errors. Schematic evolution of measurement outcomes. Square to the array of data qubits with x boundaries on the left and right and z boundaries on the top and bottom. Okay, those are the z boundaries and those are x boundaries. Okay. And then there is so aside from that, then there is also this thing. So basically that's what here James says the surface codes can also be generalized to qubits. And that's been the answer from 2018, so it's fairly recent. So what do we have here? So it's kind of the generalization, probably. To the electron layer. Is that a miracle? Fair to technical. Fairly technical. Way too technical for my current goals right now. Algebraic structure. Boo. Fancy stuff. Okay. That's not definitely something. Let me take a look at the other answer, and then maybe eventually check out one of the papers. If James says those are good entry points, then I I believe him. What is this other answer saying? So success is a little bit variable. It might refer to a whole class of things. Toric code on different lattices. It might refer to planar code, the specific variant on a square lattice with open boundary conditions. The toric code. I'll summarize some of the basic properties of the toric code. Imagine a square lattice with periodic boundary conditions. For example, the top edge is joined to the bottom edge. Okay, the top edge is to the bottom edge, and the left edge is joined to the right edge. If you try this with a sheet of paper, you'll fine, you get a donut shape or a torus. Yeah, okay. On this lattice, we place a. Sorry. How can I get out of that? Oh, okay. On this lattice, we place a cubit on each edge of a square. So it's a slightly different representation. Logical set operations, stabilizers. Next, we define a whole bunch of operators. For every square on the lattice comprising 4 qubits in the middle of each edge, we write BP XXXX. XXXX. Acting a Pauli X rotation on each of the 4 qubits, the label P refers to plaquette. Okay, so each of those squares is a plaquette. Acting a Pauli X rotation, we write these acting a Pauli X operation on each of the 4 qubits. The label P refers to plaquette and is just an index, so we can later count over the whole set of plaquettes. On every vertex of the lattice, surrounded by 4 qubits, we define AS as ZZZZ. On every vertex. So this would be these. For every square in the lattice. There's a star. S refers to the star shape, and again it will let us sum over all such items. We observe that all of these terms mutually commute. It's trivial for AS prime equals to BP, BP prime equals 0 because Pauli operators commute with themselves and identity. More care is required with AS BP equals 0. But not that these two terms either have 0 or 2 sides in common and pairs of different Pauli operators commute XXZZ equals 0. Don't really know what it means, but code space. Since all these operators commute, we can define a simultaneous eigenstate of them all. The state is such that this defines the code space of the code. We should determine how large it is. For an n per n lattice, there are n squared qubits. So the Hilbert space dimension is n to the power of 2. There are n squared terms which collectively refer to as stabilizers. Each has eigenvalues of +1 -1. Does it just know that in equal number and uncommon number has them? Defines state. So any equal number. And when we combine them, each has the dimension of the Hilbert space. So we would think that this uniquely defines a state. Now, however, observe that the code can encode 2 qubits. Okay. Logical operators. How do we encode a quantum state in the toric code? We need to know the logical operators. Stabilizers. Okay. But that's nice because here basically, okay, so there's a couple of different conventions for how to label different operators. We'll go with my favorite, which is probably the less popular. Take a horizontal line on the lattice. On every qubit apply Z. This is Z1L. In fact, any horizontal line is just as good. Take a vertical line on the lattice. Every qubit apply Z. Okay. So basically, yeah. Okay, so here we have a couple of examples on how to define certain operations on that. So logical set operations. Okay. Anion pair, basic excitation. error detection and correction. Once you have code and some key stored in the code space, you want to keep it there. To achieve this error correction, each run of error correction comprises measurement value of every stabilizer. Each A and N given us a okay, this is our error syndrome. It's then up to you, depending on what error model you think applies to your system, to determine whether you think the errors have occurred or not, and then try to fix them. Error correction threshold, while the distance of the code is n, it's not the case that a recommendation occurs. Okay, the planar code details are largely identical to the toric code, except that the boundary conditions of the lattice are open instead of periodic. This means that at the edges, the stabilizers get defined slightly differently. In this case, there's only one logical qubit in the code instead of two. Okay, so the planar code or the surface code is just a simplification or a simplified model for the toric code, in which the edges have different rules, but that limits the amount of information you can encode. Okay, but I think I'm fine enough with this so far. I don't think I want to take a look at this. I think from an introductory perspective, that's probably good enough. But it's definitely not details. I really would like to. I mean, I don't think that I need to know more. But I probably, if I would want to explore that topic farther, I know where to start now. I mean, definitely one of the other papers, topological quantum memory, because there's also this other paper that's also linked in there. A two-dimensional quantum system with anionic excitations can be considered as a quantum computer. Unit transformations can be performed by moving the excitations around each other. Measurements can be performed by joining excitations in pairs and observing the result of fusion. Such computation is fault-tolerant by its physical nature. Okay. But that's a different way of building a quantum computer. Toric codes and the corresponding Hamiltonians. Abelian anions. Yeah, that's way too technical. So I'm going to leave it here, folks. I think I'm going to leave it here. Not interested in exploring this further. Intuitively, it's basically, it's basically, that's how you try to build the logical qubits by putting them in I mean, there's different concepts that are being researched, I guess, and the idea is to try to find, good ones that allow you to both identify errors and correct them. So I think those are the two challenges. Or, someone figures out a way to engineer qubits in a way that the qubits themselves, the physical qubits themselves, are less noisy. But I don't know if that's possible. Am I happy with this? Am I happy with this? So I've done this so far. I think we haven't taken a look at. Did we start with one? What is quantum error correction? I think we didn't start with this, storing quantum information. Storing information, quantum information, the problem of quantum correction. Okay. Let me know what is the shape of Earth. And then February, it was harnessing quantumness. Because I think we started from 5. Decoding without looking. And the story so far. Okay. Yeah, that's where we started. Correcting dephasing. the maths of qubits, states and measurements. Okay. I think this is the attempt to explain a bit how the qubit works, the qubit model works. March, the Tori code part 1. This is where it gets serious. This is where I start to get into this concept a bit more. Okay, so here they define like that. Okay. In a grid pattern, what patterns of bit that is falling in squares? Some examples are below. Example label is 0. The one labeled in B has a string of ones passing through some of the squares. When this string enters a square, we add a 1 to that square sum. When it leaves, we add another 1 as long as it leaves every single square it enters. We will add 2 to the sum. Since 2 is even, the squares stay even. The only way for the string to leave every square is... Because that thing confused me here. I thought it was all the time about loops through the donut or around the donut. And that's neither. When all squares are even, the bit values look like loops of ones on a background of zeros. Doing B flips on the around loop doesn't change whether any square is even or odd. I'm trying to recap. I'm just like, because I'm not so sure I'm measuring loops. Blue also. There's obviously quite a big difference between examples A, B, and C and D. And C and D, there's loops around. C and D, there's loops around the donut. In A, B, there isn't. Is there a way we can quantify this more mathematically? These are also in a loop. The loop goes through the blue squares instead of the white ones. It also goes around the torus the other way through the donut. We'll use the blue qubits to make a measurement. We add up all their zeros and ones. I almost forgot we need a logical start if you are as possible. For this, we need to pick some set of zeros and ones for the physical qubits, the small squares in the Tori code that we associate with the zeros of the logical qubit. For this, we need to pick some sets of zeros and ones for the physical qubits. The small squares in the Tori code that we associate with the zeros of the logical qubit, and some that we associate with the 1 of the logical qubit. For the repetition code, we just pick on the physical qubits, logical 0 and logical 1. But the Tori code is a bit more complicated. This is perfect for logical modifier. For the measure involve a whole bunch of physical qubits that we need through a loop through a donut. In the Tori code, there is something that we cannot measure with just one physical qubit, whether there are not or even a number of loops around the donut. For this, we need our measurement of a whole bunch of. Okay. This is perfect. If we want our logical qubit to be 0, let's use a bunch of physical qubits with an even number of loops around the donut. Like from left to right, or right to left. So we could set the physical bits to the values in A or B. Why B? B doesn't have anything around the donut. That's what's confusing me. Or does it? maybe anything that doesn't go through the donut, it's around the donut. Maybe that's what it means. Yeah, whatever. Because vertical will be through the donut, right? If we want our logical Q to be 1, let's use an odd number of loops around the donut. Physical to be even number of loops around the donut. Okay, and B have 0, so that's why. If we use, let's use an odd number of loops around the donut. Okay, no, it's around the donut. Okay, yeah. No, that's nothing. Then that's just an example of a possible configuration. But we're only taking a look at loops through the donut and around the donut. And in this case, it's just around the donut is enough. Okay, yeah, I think it's fine. Yeah, I think I got the gist of it. So basically, you have that system, and then with these rules, you can easily detect errors because those loops get broken. And you can kind of figure out where do they exactly break, and then you can try to correct them. But it's not always trivial. I think I'm gonna leave the introduction sort of I just wanted to scratch the surface, see what was under the quantum error correction world, and I guess it's just like tens of different research areas and paths that people are trying to follow here. But it's not definitely something that I'm currently interested in. But it's good to know. It's good to kind of have checked that a little bit. So perfect.